Hello, people. Right. Okay, people. How are you? Homework, 2 questions. Clarification, anything? Not yet. Homework 1, mistakes that I've seen in some homeworks. Surprised. If I have a tree, well, I'll tell you that for every subtree, the number of nodes in the left is and the number of nodes at the right. If it has n nodes altogether, and I'll tell you that n left is larger than 0.1 n, and n right is larger than 0.1 n. The number of nodes that you have on the left and in the right, and I'll repeat it recursively. When will I have such a tree? I'll have such a tree, for example, in the case that all the I insert an element and all the elements that I picked are good pivots. Good pivots was, as you remember, picked with respect to, well, it was with respect to quicksort, what we said we have 80% somewhere in the middle, most of the elements, not very small, not very large, and if I pick an element which is not in the smallest 10%, nor in the largest 10%, then it will be a good pivot in the relationship of the quicksort, and when I build the tree, if this will be the root of the tree, then I know that the number of keys smaller than it is at least 10% of the total amount of elements. The same goes for the right. And if I have this property recursively, what would be the height of this tree? That is, every node here will have this property. Unless you have a really tiny tree with less than 10 nodes, and then it's a bit meaningless. But if you have any tree with more than n nodes, and I'll tell you that it's by this property. In the left side, you see at least 10% of the total amount of nodes, and so in the right side. In particular, it excludes the case of shreds that looks like this. I mean, it could, but only if you have at most 10. So what would be if you have n keys, what would be the general height? Log n, right? It's kind of easy, and people, somehow it shows that people are confused about it. Why is this log n? Because look at the look at some key x, and ask with how many elements x was compared to, which was exactly the length of the path to x, or look at when x is moved from one subtree to the next subtree, what is the size of its own subtree? So the size of its own subtree would be when x just about to be inserted to the main tree, all it knows is that it's in a set of cardinality n. Then I'll send it to one of the subtree. So maybe it's in a big subtree, but even if it is in a big subtree, then because I have 10% on the other side, then in the set that contains x, I have at least 0.9, 90% of the keys in this whole subtree. Go one level below it, one level below the immediate child of the root. Now X is in a set whose size is at least the set X is in a set. Let's write it down. If the path to X is of length I, then at this moment, or X was just in the process of being inserted, and it was already went after comparison with I many elements, then the size of its own subtree is I take it back, is the size of its subtree is smaller or equal than 0.9, because every time that you are going down a level, at least 10% of the elements are going to the other side. So you are left with a tree whose subtrees, whose size is no more than 90%. 10% went to the other side. That was exactly the property of good pivot. Make sense? So how deep, how long can the path to X be? Well, when X finds itself in a tree of size 1, it cannot go any lower. It must become a leaf. How soon will it become a leaf? When n times 0.9 to the power of I, this number becomes 1, which will happen when I is log n. Exactly the same log n that we saw in the quick sort plays now if you are building the tree by inserting elements at random. Okay, so that I saw a few mistakes and a few others were fine. Zoom people, can you hear me well? And do you have questions about homework 2? Let's start from the easier question. Zoom people, can you hear me? Hard, okay. Looks like they can, hopefully they can hear me. Okay, yes, great, thanks. Any questions about homework 2? Zoom? Okay, I didn't check Piazza today. I checked it yesterday. So I think that we are fine. And always people had some clarification, so I changed the online version every time that I had some tiny editorial questions. What? I mentioned it. That, I didn't change the content of anything, but people wanted to clarify, weren't clear, and I think that I was talking about the ith buckets. I had an S that confused people. It is not a set of I buckets, it's bucket number I. So I think that I made it clear. I added, and when I'm adding, usually when I'm editing the document, I'll do it in different colors, so it will be clear what's the edit. But if I don't think, if it's not a very minor updates, maybe I will not bug you about it. Okay, so that's were questions about the buckets into the throwing balls into buckets that got confusing to people. Where were we studying? Where were we with the linear time algorithms, the incremental linear time algorithms that we summarized in the previous time? We said here is your algorithm. You are you're inserting the half planes one by one, H1, H2, H3, H4. You're inserting this half plane one by one. At each moment, you are maintaining V4 in this case, which was your optimum up to this moment. You're inserting one more half planes, H5. You're checking if V4 agrees or violates H5. If it doesn't violate, then V5, the optimum after inserting 5 half planes, is just V4. So you're just calling V4, just called it V5, optimum after 5 half planes, and nothing to be changed. If H6, on the other hand, does violate V5, then what did we do? In the one dimension, what did we do? I'm adding H6, which does violate the previous solution that I had so far. I need to find a new solution, but I'm sure that it is on the line that defines H6. So I'm calling the 1D LP. And what was the probability to, so in this case, we'll call the 1D LP, say, to find V6, the lowest or the optimum point after 6 half planes. We inserted the half planes in random order. What was the probability that Vi is different than Vi plus 1? What was the probability that this happens? It was extremely similar to what we did when we looked at the closest pair. We said, since I am in 2 dimensions, and to tell you what is the optimum, it's enough that I'll specify 2 half planes. If these are the 2 half planes that I inserted, these will be the first ones that I'll insert out of the 6, then I don't need any updates. In general, I insert them in random order because I don't know what is a critical one. It's chicken and an egg. But to have the events that Vi and Vi plus 1 are different, then the I plus 1 half plane that I insert must be one of the 2 that determine this vertex. In analogy, when I inserted the points at random order and keep the closest pair, then when I'm inserting one new point, to participate in the new closest pair, it needs to be one of the pair that is the closest one, and the chance that it will happen would be 2 over I plus 1 in this case, if it's I plus 1. Because there are only 2 special ones. And once again, the moment that I told you what makes them special, meaning that if I'll show you a set of these I plus 1 half planes, 6 in this case, you know what is the optimum. The optimum has nothing to do with the order of the insertion for this particular 6. Meaning that if you know what is the optimum for this particular 6, then you also know what are the 2, we called it the 2 red balls in this set of 6 balls or 6 half planes. 2 are special. What makes them special? In this problem, they are the 2 that determine the local optimum. But in the closest pair, it was the 2 points that are the closest one, whatever. Something about them is special. You'll see them in the set of inside this set, these are the 2 special ones. Now take any random permutation of these 6 half planes. What's the chance that one of the 2 red balls will be the last one? Well, it's 2 of them. Why 2? Because I live in 2 dimensions. To determine a vertex in 2 dimensions, I'll need 2 half planes. To determine a vertex, the optimum is 3 dimensions. When I have half spaces instead of half planes, I need 3. D dimension, it would be D. Okay, 2 are take a random permutation, what's the probability that A will be the last one? If altogether I have I plus 1, then the probability that A will be the last one is 1 over I plus 1. Probability that B will be the last one is 1 over I plus 1. So the probability that one of them is the last one is 2 over I plus 1. What's the expected work at the ith step? The expected work at the ith step is what's the probability that this happens, which is 2 over I plus 1, times how much work do I need to spend if I do need to call the 1D LP. The 1D linear programming, solving it on a line, just takes this set of half planes. It takes linear time. You need to find the maximum and the minimum of two sets. But it's linear in what? It's linear in I, not in N. So the work that I need to spend at this step is only I plus 1 times a constant. So that's the probability that this extra work needs to happen. That's the amount of work that you need to spend times the constant if this event does happen. What's the expected work? These two cancel each other, so the expected work at the I step is a constant, and hence linear time algorithm. What are we doing in 3D? In 3D, the only difference was that we are adding the planes one by one, the half spaces now. It's not half planes, it's half spaces. That is an example, all the set x, y, and z such that z is larger or equal than x plus y. That would be an example of such a half space. That's the only difference. The boundary, Li, is now instead of being a line, the boundary is a plane. What do I do in case of a violation? I'm adding age 6, and it violates the previous optimum solution. I need to now look for a solution, but a solution where will be the new optimum. It will not be floating anywhere in 3D space. It will be on the plane that bounding age 6, except that age 6 is now becoming a half space, not a half plane. And L6 in 3D for example, in this case, the boundary will be all the x, y, z, such that z equals to x plus y. Right? By the way, that's my z. It's, that z equals to x plus y is exactly the half plane. It's exactly the plane that bounds the half space age 6c. And what do I do if I have this problem or find the solution on this plane called the two-dimensional linear programming? How does the two-dimensional linear programming works? It's called from time to time the one-dimensional linear programming. And now you know how to solve it in linear time, also in 3 dimensions. And because now the probability that vi plus 1 is not vi, help? And so, yeah? Superb. The optimum is not determined by 2 special planes, but by 3 special planes, half spaces. That's the only difference. OK. So overall, the running time, we can show that in d dimension and half. if I'm living with n half spaces, and I live in d dimension, reals to the power d. That is, in the diet problem, it would be instead of having only oranges and bananas, you have oranges, bananas, avocados, schnitzels, whatever. D types of foods. And the running time will be order of n, which makes us happy because it's linear in any dimension, times d factorial, which says that it's okay if d is really low, 4, 5, 6, it's fine. It's still a very fast algorithm. Okay. I don't expect you to prove it. You're basically just solving the running time, the recursion formula, but now it's recursion formula with two variables, n and d. This is the solution, n times d factorial, so linear in n in any dimension. But if the dimension becomes a bit higher, then you probably want to use a simplex. Simplex algorithm has theoretically exponential running time. In practice, it works very, very well in any dimension. Just use a library that calls the simplex algorithm. For example, as students, you can use Cplex, which is a library that owned by IBM. And Cplex as a library which is free as students with some limitations about how large and how large the problems that you're solving can be, or if you're using it for research. And Cplex has an implementation of the very basic simplex algorithm. It is kind of gradient descent, a clever gradient descent in the feasible region. Don't forget what is a feasible region, but now in much higher dimension. And simplex will solve linear programming in realistically almost always very, very fast for any problem you have in mind. Quick question before I continue. Is a feasible region always connected? Feasible region, just to remind you, we had in the diet, it was all the diets that were healthy. You had it also in the homework, and then you had the cost function that asked for the vertex of this polytope or polygon that is the cheapest one. But the feasible region was just all the points that all the half-planes agree with. By the way, I can always take the diet problem and ask just what is a feasible region if I'll add the constraint that my budget is at most $70 per day for food. What is, yeah, it's too much. What then is a feasible region? Is a feasible region is empty or not? But then I don't have a cost function so much. I can take arbitrary cost function. I just add it as one of the constraints. My diet needs to satisfy all the vitamin constraints and budget constraints. Just add one more budget. And by the way, you note that all these algorithms are very, very tolerant to the number of constraints. If you're going up in the dimension in any problem, you'll really notice it. If you add more unknowns, you'll notice it in the running time. If you're adding more constraints, it's only linear, neglectable. So the question was, in the feasible region, all the points that lies in all the half-planes, feasible region, is it necessarily connected set? That is, if I have 2 points that are in the feasible region, 2 points which are both in the feasible region, either a path between them that consists of points that are also feasible. People say yes, and the argument is very simple argument.
The region is convex?
Convexity. Not only that there is a path, but there is a segment between them lies inside each one of the half-planes, half spaces, and hence it lies in their intersection. Each set is convex. Give me 2 points in the set. The segment that connects them is also in this set. That's to be convex. And if 2 sets, A and B, are convex, then if each one is convex, then the intersection is convex as well. So yes, that explains why the feasible is unique. It also explains why local optimum is also the global optimum. Why gradient descent? What are you doing in gradient descent? Like the simplex, you are following the boundary until you hit the lowermost point. Follow the boundary until you hit the lowermost point. Putting under the rug lots and lots of details. Pick a direction that you are on the boundary. Like, think about this is my feasible region. It defines by 6 half spaces. One comes from here, one comes from here, etc. I'll pick a point that might be somewhere. I'll try to get to the optimum part. I'll pick a point somewhere on the polytope in the feasible region, and I'll move along it until I'll hit an edge. Then I'll move along this edge until I hit a vertex, continue moving along this edge, but keep going until I hit a vertex that I cannot improve anymore from this vertex, at least not by local movement. And because it's convex, the box is convex, or the feasible region is convex, then the local, or a local minima is also the global minima. So it's only one minima, only one point that you cannot improve. There could be a lot of points that are equally good. I'm not saying that a vertex is the only solution, depending on your cost function. But at least one of these vertices is the optimum, and it's a local optimum as well as a global one. OK, moving along. So sometimes we want linear programming. Sometimes we want to have the constraint that some of the that we don't want to buy 3/4 of a banana, or so we want to solution where the optimum will consist of integer values. Some or all the variables, I'll ask them to be an integer. And then, in addition to have just normal linear programming problem, by doing so, I will convert the problem into some form that maybe will be less intuitive when I first look at it and quite artificial. But the good thing is that there are libraries that solve ILP for you, namely the simplex that I mentioned a few times. And there are thousands and thousands of man-hours that invested in optimizing this part. And if the ILP, integer linear programming, comes back and tells you, this is my optimal, this is the solution to the problem, then you can trust it. It is the optimum solution to the ILPs that you gave it. OK. So let's see some examples where we are using ILP to other problems. Bipartite magic. What is bipartite magic? Yes. We have a graph, and this graph is bipartite. It has two sets, all the vertices. I can break all the vertices into two sets. One is A, one is B. For example, teachers and courses. And I'll say that there is an edge between a teacher and a course if this teacher can teach this course. If this teacher cannot teach this course, then there is no edge in the graph between them. And to make the graph a bipartite graph, it needs to have the property that every edge connects one vertex of A to one vertex of B. I don't have any edge that connects to B's. I don't have any edge that connects to A's. What is a matching in this graph? It's a subset of the edges, such that every edge in the matching connects a vertex of A to a vertex of B. Well, it's bipartite, that's obvious. And at the same time, one vertex of A is not on not on two edges of the matching. And same goes for B. One vertex of B is not adjacent to two red matching edges. Like you want to assign one course for one instructor to one course. You don't want the case of a course taught by two instructors or an instructor that teaches two courses. That would be an example of one-to-one matching. Okay. Now, we'll see there is many ways to solve the problem of finding a matching in this graph. We can start, for example, by greedy approach. Let's look at that's a classical example. Here is my graph. Here is a set A, A1, A2, the set B, B1, B2. Greedy approach might say pick an edge that connects two exposed vertices that are not in the matching. If this edge connects vertices that are not in the matching, add it to the matching. So I'll pick, say, the edge A1, B1 to add it in the matching. And I'll try to see if I can find more edges in order to teach more courses, to keep more instructors from poverty. I'll see that this edge is free. This edge is free, but I cannot add it to these edges to the matching. So greedy will not be optimal. If I wouldn't start from this edge, it was a bad choice for the first edge to start. If I would start from the edge instead, if instead of starting from A1, B1, I would start from the edge A1, B2, and then notice that A2, B1 is still free, and now I have matching of size 2. Two edges in my matching. So there are a lot of ways to solve bipartite matching. You can phrase it as a flow problem. Later today, you'll know what are flow problems. You can use augmenting path. And you can find a lot of libraries that solve bipartite matching. But let's say that you are lazy to check out of all the libraries, and on the other hand, you have Cplex already installed, connected. You have the connection to ILP. Let's see how we can phrase the matching problem as an ILP. So I'm going to use a set of variables here. It will not be in a fixed dimension. I'll basically look at the edge, look at the graph, and for every edge in the graph, for every edge, I'll assign a variable for this particular edge. For the edge E3, there will be a variable, namely x3. E2 will have a variable x2, and so on. Now, what are the linear half planes, linear constraints that I'm going to add? I'm going to correlate the linear programming and the integer linear programming that I'm going to generate. I'm going to correlate it by an argument between me and myself. There is not correct or incorrect. It's you have to decide what is this. How do you express a solution from the linear or integer linear programming? How is this related to the problem you started with? So what will be the argument that we are doing? We'll say that xi, xe for the edge e, will only have two possible values. It will be a Boolean one. And if x is 1, then e will participate in the matching that I'm going to produce. I'm after finding a matching, finding a set of edges as large as possible so that no two edges of the matching connects to the same vertex. So I'll make sure that xe is 1. I'll understand it as the edge is in the matching that I'm going to produce, and xe is 0 if, of course, then this edge is not in the matching. And now let's see what is the ILP that I'm going to phrase. And remember, it's some effort to understand what I'm doing here, but once you understood it, and you see that this is a moment that you're taking this problem, you start from the graph, you're generating this problem of set of constraints, you're pushing it into the library and outspits the vector, the values of the xi, xe, that will tell you which edges to use in the matching and which not. So am I teaching you an algorithm to solve this problem? Yes and no. I'll teach you how to use Excel, if you wish. Just it's not Excel, it's simplex. It's so how can I force xe, oh, typo, it's xe. How can I force xe to be a Boolean value? First, I want to tell, I'll give two linear half constraints for every xi. I'll say xi is larger than 0, and xi is smaller than 1. Making sure that xi is between 0 and 1. And then I'll tell the ILP also that I want for every I insist that xi will be an integer. So being an integer and at the same time being between 0 and 1 doesn't leave xi a lot of options. It's either 0 or it's 1. Yeah?
What's the difference between I and E in this scenario?
Not really. It's x of ei to be precise, but then it would force me. xi, no, we'll write it. xi would be a shorthand of calling it x of ei, and it's just the variable that I'm using to tell me if the edge ei is in the matching or not. Just didn't want to run with tedious sub indices. Okay, but that's definitely xi or xe, whichever you want, for every edge in the graph. And these constraints plus the requirement that xi is an integer will force it to be a Boolean, in the matching or not. It will be in the matching or not, but so far I didn't tell the ILP anything about a matching. I just said, pick a set, here are your set of variables. I should also tell it what is my cost function. My cost function is I want as many edges in the matching as possible. I want to have as many edges in the matching as possible as long as it's a matching. If you wish, another story about the matching, if you want, for the same graph, that a set of males, sets of females, we are only allowed matching in this part, and you are only allowed for people to be matched with people they know. Okay, so that would be another story behind the matching. And okay, so how do I only limit the solution to, what would be my cost function? I'm trying to maximize the sum of the xe's. There is a cost function when you tell the ILP what it is. It's just 1, 1, 1, 1, 1, 1, 1 for each one of the variables. What? Each xi that is on, that is 1, it means another edge will be in the matching. But finally, let's get to the constraints. What are the constraints that enforces my solution to be a solution to the matching problem? Here we're getting to the third solution. Look at the vertex. I don't know if this is a new microphone or that it's a setting. I noticed that the sound, once we switched between the wireless microphone, the sound in the recording became pretty bad. So I was trying to mess up with this today, but I'm not sure what it caused. So here is an edge, a vertex, here is a vertex, A1, and here are 3 edges that are connected to it. Let's call them E1, E2, and E3. There are 3 variables that A1 needs to know about: X1 and X2 and X3. X1 said, are we using the edge E1 in the matching? X2, are we using the edge E2? X3, are we using the edge E3? How can we say that you can use at most one of the 3 edges? We want to say only one of the 3 values could be 1. But I want to express it as a linear constraint because it's still a linear programming, except that I'm only allowing integer solutions. How can I do it? I'll say x1 plus x2 plus x3 must be smaller or equal than 1. Correct? In this way, since every xi is a Boolean, either 0 or 1, it will be impossible that both edge E1 and E2 will be in the matching. So in general, for every vertex, I will look at all the xi's such that the edge E have this vertex V as incident to the edge. I'll sum them up, sigma of xe, and I'll require it to be smaller or equal than 1. That is, it's possible. A good homework question here will ask, how can I make sure that I'm only getting perfect matching, that everybody is matched? Which would now mean that I will require it to be exactly 1. Right? That would mean that everybody must be matched. What happens if some teachers are willing to teach 2 courses, but every course must be taught by 1 course? Then depending on which vertex it is, if it's a vertex of the teachers, maybe a teacher can teach 2 courses, but a course must be taught by 1 teacher. So we'll have different types, whether it's 1 or 2. What happens if every course, what happens once again, if it's only courses and we earn WI dollars to teach the course EI. Not if EI or to teach or to have the edge or to have the edge EI in the course. Let's say if every edge is coming up with a weight and I'm looking for the weighted matching, I'll stop giving it a stupid excuse. Every edge has a weight associated with this, and I'm trying to get a matching that gives me the maximum weight, sum of the maximum weight. What do I change in the ILP? Max of
the sum of WI or WEI.
WI times XI. If I'll teach this course, then I'll earn this amount of money. Okay. If I want to have actually these courses, I'll need to have other variables that will indicate for every course, is this being taught or not? And the variable, I mean, let's do it. It's a good exercise. If the cost is associated with the, is this course being taught, what will I do? I'll have another set of variables for every Vj. I'll have a variable Yj. Also Boolean between 0 and 1 that ask, is this course taught? Is this how I spell taught? Is somebody? Yeah. Is this course taught? And I want to maximize now the sum of the yi wi. Now notice that here the sum is from 1 equal 1 until n, until the number of courses that I teach. Well, wi, and how can, and I need to make sure that yi is 1 only if one of the vertices, one of the edges that connects to this course is 1. How can I make sure that for this course, for 545, of course, we'll say y1 is asking is 545 is taught. How can I make sure that it's taught only if somebody is willing to teach it? I'll say that yi is a, if these are the three courses that can teach it, that x1, x2, x3, that yi is small or equal nice example, just the thought about it. What happened from here? What did I say by imposing this constraint? That I'm trying to maximize all the yi because I'm getting some dollars if I'm teaching this course, fixed amount, by some instructor, I don't care by whom. So I have these variables that don't correlate to anything, doesn't correlate to the matching, namely the yj for every course j. How can I make sure that the course is taught only if one of the edges that are related to this course is being taught? I'll say yi is smaller or equal than x2 plus x1 plus x2 plus x3, where x1, x2, x3 are the edges that connect to this course. Why? Because then if nobody's, this edge is not in the matching, and this one is not, and this one is not, these three values are 0, then 0, 0, 0, and yi has only the chances of being 1 or 0. Then obviously, if this is 0, then yi could be 0. So you are trying to maximize the sum of the wi, yi. I'll let you figure out the details. It's a homework, but that's the type of exercise that are very easy to do. Now, is ILP, everybody understands what I just did? I just created more variables and I forced them to be 1 or 0, but a variable that said this course is taught is 1 only if one of the edges that are leading to this edge is picked. That is, xi of one of the edges that are leading to this course is picked. Back to our standard non-weighted matching. Everybody understands these constraints? Sigma of xe for which edges? All the edges E such that E is incident to the vertex V. For every vertex V, either A or B. Now, is this the fastest algorithm to solve maximum cardinality matching? It is not. ILP is not polynomial in general. It runs fast because it's really optimized very, very well. But it's definitely not polynomial. And this problem, you can solve in n³ time, and it's very easy exercise to find maximum weight matching. So why do I tell you about matching as my first example for ILP? Because I think that I convinced you that there is many changes that you can make to the problem that would require very different algorithms for each one if you don't want to use ILP. To find a weighted maximum matching, every edge has a weight, and I'm trying to maximize the sum of weights of the edges that I'm using. The maximum weight matching is, in general, much harder than the maximum cardinality matching, where I just count edges. When we had the ILP, what did it change? Beforehand, we had just sigma of xi, sigma of xi for the unweighted case. For the weighted case, we just multiply it by the weight of the edge. Correct? We wanted to assign edges to some other variables. That was really easy, right? Just assign it with condition to something else. Now, there is a polynomial algorithm to solve at least some of these problems. But in many cases, if you have the ILP handy, that would be your quickest solution. Another point, there is also matching in a non-bipartite graph. I'll give you a graph, set of vertices, and find a set of edges so that every vertex, not correlation to A or B, any vertex is adjacent only to one edge in the matching. A vertex might be adjacent to a lot of edges in the graph, but only to one edge in the matching. Okay, there are polynomial algorithms to solve it. Professor Casasiagolo, I think, implemented even one of them. It's far from being trivial to actually understand them, to implement them, to make them run. You want a solution for maximum weight matching in a non-bipartite graph. Just run this problem. It's exactly the same problem. You just, and the ILP doesn't know at all whether it's a bipartite or not. So just to summarize it, you tell the ILP, here is a set of variables, x1 dot 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 xn, a vector of variables. Here is a matrix that represents all my constraints. Here is a list of the variables that I want to behave as an integer. Not all of them have to be integers. You can leave some as real values, so it's mixed integer. Call the ILP, you're getting the values of the xi's as a solution and use it now to generate the matching. Okay, max cardinality, we just covered it. Let's talk a bit more computational geometry. This is a polygon. This is a floor plan of our building over here. That would be the floor plan of our building. And I'll say that 2 points can see each other if the segment between these 2 points doesn't cross any walls of the building. This is a floor plan of our building, and I want to place cameras, and cameras cannot see through walls. Or I want to place antennas, and the walls obscure some of the energies of the antenna. Not everything penetrates walls, depending on frequency, and so on. So if I place a camera at a point V, here is a set of vertices that this camera sees. Okay, so if I place the camera at V, it sees the vector, the vertex M of the polygon, 1 point on the building. It sees a point B in the building. It sees a point C. If I place this point elsewhere, let's say where I'll stack it. If I place this point right over here, and I'll move GAB, then you see that it sees just this vertex, this vertex, this vertex, and this vertex. So what would be the art gallery problem? Art gallery problem would be you're given such an environment. Maybe it's a simple polygon. Maybe it's polygon with lots of hole. Maybe it's terrain. Maybe it's a 3D environment, buildings with 3D structure. Here, for simplicity, I'll just assume that a vertex that I want to place guards, cameras or antennas. I want to place guards that would be either cameras or antennas, and there is some set of candidate locations. My candidate locations here will be just the vertices of the polygon. So I can place a camera here in this simple example just at a vertex of the polygon. But the polygon has lots of vertices. And I want to make sure that each one of the vertices is observed by at least one camera. There is one camera that watches it. Why does it called art gallery? Because there are paintings at these points, and you want to place guards that will watch the paintings and see that they are not stolen. But it's really, really fundamental problems in sensor locations and antenna locations. Okay, so at the moment I'll say you can only locate guards at vertices and you're only watching vertices. But if I'd like to make it a bit more general, I'll sprinkle more points that will use either as a feasible point. I'm placing a camera only if I have power to feed it, only if it feeds something, and I'll add some other visibility constraint, and I'll add more witness points that I need to see all of them. Okay, just to see that I don't limit my generality here by saying that only from vertices to vertices. Okay, and I want to find the minimum set of guards, minimum set of vertices, so that every vertex is seen. That is, place cameras as few as possible only at vertices, so that every vertex is seen, either by the camera that sits on the vertex or by some other camera. Let's say, if the polygon is convex, how many cameras do I need just to see that you're alive? Just one camera. If could it be that I need one camera even if the polygon is not convex? Example?
You could just draw a square and then add another point and move it down, and then as long as that angle is up to
every star-shaped polygon, which is exactly, you talked about one, you just added it to all places. Star-shaped polygon is a polygon that can be seen from one point. It doesn't mean that no matter where I'll place the camera here, I'll see everything. But at least there is a point that sees everything. Like any interesting problem in the world, finding the art gallery problem is NP-hard. The fastest approximation algorithm is by my colleagues and mine from about 20 years ago. And, but let's see how we solve it with ILP. Why do we solve it with ILP? Either because we have other algorithm and we want to say our other algorithm, other heuristics, we want to compare it to the optimum. And ILP is guaranteed to give you the optimum. To the problems that you'll give it, it might take a lot of time to run, much likely. It will take little time, but it will spit eventually the optimum. So what are my constraints here? Now, I think that by now you start to get the drill. I'll first compute for every vertex, I'll see what is the visibility region of this vertex. Where did it go? should have used. You have the link for every vertex. The vertex E sees as a vertex C, D, F. If it's readable, it's probably not. These are all the vertices that I can see from here. Here are the list of vertices that I'll see. Here are the list of vertices that I'll see had I put a camera over here. So I need some time before that to compute what is a visibility region, what each guard can see. That's done in polynomial time, even efficiently. That would be the visibility of I will be the set of vertices that vertex I sees. If I put n in this vertex, what are the other vertices, including itself, that it sees? And that's the only condition that I need now to make it an ILP. Why? What will I say? My variables, just as before, are xi's, where xi is a variable between 0 and 1, where if it's 1, it means the vertex I will be in my guarding set. I'll put a camera on it. And if xi is 0, then I don't put a camera there. I want to place as few cameras as possible. So sigma of xi, namely running over the vertices and ask for each one, are you in the guarding set or not, should be as small as possible. What's my constraint? As before, xi should be between 0 and 1 an integer, making it a Boolean 1. And what does this constraint mean? The sum of xk, where k belongs to the visibility of I, should be larger or equal than 1. For every I, every vertex I, I'll assume here that I see you if and only if you see me. So I am meditating on vertex I. I look at all the vertices that sees vertex I. What's the condition that somebody sees vertex I? At least one of the vertices that sees vertex I, we really need an example here. That's too hard. Yeah, well, that's a good example. Here is my polygon, ABCD, and the visibility of A is ABCD. Everybody sees A. Visibility of B is the same thing, ABCD, but visibility of C is AB, but not C. Visibility of C, but not D. Visibility of C is C himself, herself, itself, CAB, and visibility of D is A, B, and D. And let's, so I have 4 variables here. XA, XB, XC, and XD. And my constraints should be that, if I meditate on the last one, look at the vertices that watches D. That who is potentially sees D. D itself, so XD plus XB plus XA, this plus 0 times XC plus XD should be larger or equal than 1. Why? Because if none of these 3 guys is picked, if this is 0 and this is 0, and this is 0, then D will stay unguarded. And somebody will see it and will never know about it. Okay, so for these 3 vertices, one of these 3 must be picked. and I'll write similar constraints for each one of this part. My cost function would be to minimize xa plus xb plus xc plus xd. And the ILP will discover for us that if I'll set xa to be 1 and everything else to be 0, then I guard everything. Cool. So that's how it's solved. And another problem that is well known to be NP-hard. Let's see how it helps us with network flow. So it's a good introduction to one of our other topics of this course, which is flow in a network. But our first algorithm to solve network flow will be used LP or ILP, depending if you insist on integer or not. So what is a flow problem or flow network problem? So first, what is a network? It's a graph, directed graph, where every edge has some capacity on this edge. And in addition, I have two special vertices, the source and the sink. The sink is denoted by T because S is taken. So it's the source and the sink. You have the capacity of every edge. What is the capacity? How many bits per second can I send? Or how many gallons of water can I send along this pipe? How many bits can I send along this fiber optics link? That's the capacity. I can send 0, I can send a bit more, but the 3 over there implies no more than 3 gallons per second along this link. Okay, let me go on. You have the PDF. What am I looking for? I'm looking for a set of values, which I'll call the flow. And it's a flow in computer science. Flow in EC has slightly different meaning. I'll look for a flow in the network, which is what? I'll tell you for each edge how many gallons per water you want to send over it. Your overall problem is, of course, send as much data from S to T, or as much water from the source to the sink. That's Netflix. It rented a bunch of fibers along its way. How do it utilize it in the best way to send data to the customer over here? OK, now, what are we looking for? What are our variables here? The variables will be, for every edge, tell me what is a positive flow. There will be something that maybe we'll discuss later in the course that will be the negative flow. Don't worry about it. It's only the positive flow right now. Some number between 0 and larger than 0 that will be for every edge UV in my graph, every edge UV in the graph, remember directed graph, you need to decide about the value or the flow across this edge, across this link, across this pipe. PUV will say how many liters am I sending on this pipe directly. And now, what are my constraints? I have two types of constraints. One constraint will be the capacity constraint. What you need to send must be positive. You're sending it across, every pipe has one direction. You can have another edge going in the other direction, but the pipe doesn't care about it. It's one directional, it needs to be positive, and it cannot exceed the capacity of this pipe. CUV is the input capacity of the pipe. You cannot send more than 2 liters across this pipe. You cannot send more than 3 liters across this pipe. But possibly you want to send less. So one type of constraints would be the capacity constraint. The other type of constraints will be the flow conservations. Look at the vertices. They are routers. They are memory-less routers. If you have Belgian students here that stores data in the routers, we don't, not in this case. Meaning that all the router is doing is take the water that comes in and decides how much of it is going out across every pipe. Putting it algebraically, for every router, which is not the source, of course, because the source generates data. It's not the sink, because the sink wants to take the data out, takes the water out of the system. But every other vertex that is not the source and the sink, the flow conservation says, look at the amount of flow that goes into D. It takes 1 gallon per second across from S directly. Another gallon comes from B, so it has 2 gallons, meaning that in every second it needs to get rid of at least of these 2 gallons, exactly these 2 gallons. What comes in must goes out from every router. So it only can send data across this link in this direction. So if it's 1 plus 1 comes in, 2 goes out. And this pipe, by the way, is saturated. But what about B? 1 goes in plus 2 goes into B. How much goes out? 2 plus 1 goes from B into G and into D. Make sense? And so on for every other vertex. That is the sum of the flow that goes into a vertex equals to the sum of flow that goes out from the vertex. And the linear programming just writes itself. I just told you what is exactly the integer programming that will solve the flow from you. You'll try to send the maximum flow. What's your variables? The variables are these values PUV. We are 30 seconds away from that. PUV will just be the variable. What's your constraints for every vertex in the middle? Every vertex that is not S and not T. The sum of the variables going into the vertex equals to the sum of variables going out from the vertex. So if you write it here as a matrix for the ILP, it would be a set of positive ones for the incoming edges. Negative ones for the outcoming edges should be equal to 0. And what about this one? For every variable, it must be positive and no more than the capacity, which is another input. And that's it. Much more general and much more easier to generalize than the Ford-Fulkerson or other polynomial algorithms that we hopefully will discuss, but are more limited about what can this. But it's not necessarily polynomial. If you insist that the flow are integers, then of course you can just add it. You are saying it's not bits, it's tracks that are moving here. And I cannot send 0.3 of a track that goes over there because I cannot split a track. Then you're solving the same issue now with cars or with trucks. Just now, the numbers that you're getting will be the integers that you say. I want my flow only to accommodate these values. And so on. So in the next meeting, we'll go over a few problems that we can solve using flow problem, in particular matching by itself, and we'll, yeah. Okay, we will continue. Bye. Okay, any questions? Good. Okay.